Chapter 3, Loci. Now, a locus is the position of a point or the path followed by a point as it moves. This could be a straight line or a curved path. Let's look at the common loci. 1. Locus of a point at a given distance from a fixed point. For example, find the locus of a point 3 centimeters from X. In other words, we are finding all points that are 3 centimeters from X. If you draw a line 3 centimeters from X, then the end of that line is one of the points. But it's not the only one, because we can draw endless number of lines 3 centimeters from X in all directions. In fact, the locus of such a point is the path around a circle of radius 3 centimeters with center at X. So we take a ruler and measure 3 centimeters using a compass. Put that away, and then we draw a circle, and any point on that circle is 3 centimeters from X, and it is the locus we are looking for. And so the locus of a point that moves in such a way that it is always at a fixed distance from another fixed point is a circle. Number 2, locus of a point equidistant from two fixed points. For example, find the locus of all points equidistant from A and B. If you draw a line AB, you could think that the locus of such a point is the midpoint of the line. And you are right, but it's not the only one. In fact, such a locus is a perpendicular bisector of AB. So we construct a perpendicular bisector of the distance AB. Place the compass at point A. Open it to more than half the distance AB. Move it up and draw an arc. Move down and draw another arc. Without changing that distance, place it at B. Draw an arc. Move up and draw another arc. Now join the intersections and we shall have the perpendicular bisector. Initially, it seems logical to think that the midpoint of A and B is the locus. But now we are saying that the locus of such a point is a perpendicular bisector. All points along that blue line are equidistant from A and B. Think about it this way. If you draw a line from A to the bisector, and then from this point C to B, you will have an isosceles triangle. And AC is equal to BC. And you can draw infinite number of isosceles triangles on either side of the line. And so the locus of a point equidistant from two fixed points A and B is the perpendicular bisector of AB. Thirdly, the locus of a point at a fixed distance from a fixed line. For example, find the locus of all points 3 centimeters from AB. Initially, it would be sensible to think that such locus is a pair of lines on either sides of AB, both 3 centimeters from the line. That's correct, but there is more. You need to know that even the ends of the line, that's point A and B, still make part of the line. And so the locus extends not just above and below the line AB, but also on the left and the right sides. And so the thing to do is take the compass and first measure 3 centimeters. Place it at A and draw a circle. All points on that circle are 3 centimeters from the end of that line. Do the same with B. You can now draw tangents to the two circles, but just to be sure, you can draw a third circle with the same radius. It's not a must, it's just to confirm. And so all around on those lines is the locus we are looking for. Number 4, the locus of a point equidistant from two intersecting lines. Find the locus of all points equidistant from AC and AB. Now, if you draw an angle bisector of angle BAC, any point on that bisector will be equidistant from the two lines. And so place the compass at A, take any distance, and make arcs to intersect both lines. There and here. Place the compass on one point and make an arc. Maintain the same distance and come to this other point and mark a second arc. Now join the vertex to the intersection. That is the bisector, and all points on that line are equidistant from AC and AB. And so the locus of a point equidistant from two intersecting lines is the bisector of the angle between the two intersecting lines. Next, number 5, intersecting loci. Now, sometimes different loci could have a common point or even a region. For example, find the locus of a point 6 centimeters from A and equidistant from AB and BC. So the point or points must satisfy the two requirements or conditions. First condition, 6 centimeters from A. We've said the locus of a point at a fixed distance from another point is a circle. So, we measure 6 centimeters and then we draw the circle. Second condition, equidistant from AB and BC. We've said that such a locus is the angle bisector, and so we bisect the angle at B. Place the compass at B, arc here, and arc there. Go to this point and make an arc there, go up and make an arc also. Now draw the bisector. There. All that is left now is to show the points. 6 centimeters from A is anything lying on that circle. Equidistant from AB and BC is anything on the red line. So 2 points satisfy both conditions, this point and also this point. Another example, find all points that are more than 4 centimeters from A and nearer to CD than BC. Condition 1, more than 4 centimeters from A. So we first find 4 centimeters from A. We measure 4 centimeters and draw a circle at A. And so anything outside that circle must be more than 4 centimeters from A. Next condition, nearer to CD than BC. If you have to find that, we first construct the line that is equidistant between them, and that's an angle bisector. We bisect the angle at C. Mark an arc and another arc here. Come to this mark and make another arc there. Come down here and mark another arc. Good. Now draw the bisector. Now all region above that red line is nearer to CD than BC, but we cannot include this area because it won't meet condition 1. And so really, the area we are interested in is this one here. We take 2 examples. First one, ABCD drawn to scale is a rectangular garden. A tree is to be planted such that it needs to be at least 15 meters from point A and at least 20 meters from the side BC. Find the region where the tree could be planted. First condition, at least 15 meters from A. First we find all points 15 meters from A. By now you know that that is a circle. From the scale, we shall measure 3 centimeters on the ruler. Go to point A, place the compass there, and draw a part of the circle that will be within the garden. You don't need the entire circle. So all points on that arc are 15 meters from A, and so we need at least 15 meters. That means the closest the tree can get to A is 15 meters, and so we need all points on that arc and beyond. Second condition, at least 20 meters from the line BC. The locus of a line is another parallel line. So I measure 20 meters from BC. That should be 4 centimeters on the ruler. I need to get rid of these rulers. Make a parallel line to BC through this point. So this line represents all points that are 20 meters from the line BC. This is the closest the tree can be from BC. And so we need all points on that line and beyond, but not beyond the arc. So the tree can be planted anywhere in this region. Another example, a farmer wants to build a store to be at most 30 meters from A and at most 35 meters from B. Show the region where it could be built. From the scale, 30 meters will be 6 centimeters on the ruler. We measure that 6 centimeters. The locus of a point from another fixed point is a circle or a part of a circle. So we draw an arc. I could have drawn the entire circle, but I can actually predict the region, so I don't need the whole circle. 35 meters from B. That will be 7 centimeters on the ruler. Go to B and draw an arc. Looks like my first arc isn't large enough, and so I will have to enlarge it. That's okay. We don't need these tools anymore. So the store can be positioned anywhere in this region. Next, lockers involving codes and arcs. Now, consider this circle on your screen. A and B are random points on the circumference. A line joining A and B is a chord. The chord subtends an angle A at the center. Find the locus of a point P such that angle APB is equal to a half angle A. From the chapter on circles, chords, and tangents, we know that the angle subtended by a chord at the center of a circle is twice the angle subtended by the same chord on the circumference in the same segment. And so if chord AB subtends an angle at the circumference, it will be a half angle A, and that point P can be anywhere on that major arc. And so the locus of P is the major arc AB. The constant angle locus. Again, we know that a chord of a circle subtends equal angles at the circumference in the same segment. AB is a chord and P is a point on the circumference of a circle. As point P moves along the circumference, the angle APB remains constant. The locus of point P is the arc APB of the circle. And finally, loci of inequalities. We have used graphs to solve simultaneous inequalities. The same graphs can be used to describe loci in the Cartesian plane. For example, describe the locus of all points such that x plus 4 squared plus y minus 5 squared is less than 9. The boundary line for this inequality has the equation x plus 4 squared plus y minus 5 squared is equal to 9, and this is the equation of a circle. And so we have x plus 4 squared plus y minus 5 squared is equal to 3 squared. The general equation of a circle is x minus a squared plus y minus b squared is equal to r squared, where a and b are the x and y coordinates of the center. Relating the two, a is equal to -4, b is 5, and r is 3. And so it's a circle with center at -4, 5, and a radius of 3 units. And so that is the circle. We now need to know which side to shade, inside or outside the circle. We take a test point and substitute in the inequality. We take 0, 0. 0, 0 is outside the circle. So let's see if it falls within the required region. If it doesn't, we shade the entire region outside the circle. 0 plus 4 squared plus 0 minus 5 squared is less than 9. 16 plus 25 is less than 9. 51 is less than 9. That is not true. And so we shade the outside of the circle, because the outside of the circle falls within the unrequired or unwanted region.
I believe with the right resources and help, most people can learn most of the math that they need to learn. But in almost any class that you go into, you need to make sure that you're at the starting point. People come in with different backgrounds, different preparations, and so you're not all on the first day at exactly the same place. And so you can go on and learn math. You may need tutorials, you may need tutors, etc., to get your foundation solid so that you can build the next course on it. But math is not so complicated that most people can't learn high school math and certainly the introductory courses in university.